Okay, I wanted to start talking about Chapter 4 of John Grimma's stuff, so you should see that stuff online. Chapter 4, we'll be talking about linear and quadratic functions. Okay, in Section 4.1, he introduces linear functions here. I'm not going to spend too much time on this because this is something you should have seen already in intermediate or even beginning algebra here. But let's go ahead and go through a quick review. A linear function is going to look like this. Y equals f of x equals mx plus b. M is a constant, okay? And this is slope. This is the slope of the line. And b is also a constant. This is the y-intercept. That is the y-coordinate of the point where the line crosses the y-axis. Okay, so if we were to graph this thing, sort of as a rough graph here, the line might look something like this. Okay, here's the x-axis, here's the y-axis. And this point here, when x is 0, you can see if I let x equals 0 in here, m times 0 is 0 plus b is b. This is actually what we're calling the y-intercept. Some people might say b is the y-intercept, like I've done here. Other people might say the point itself, where the line crosses the y-axis, is in fact the y-intercept. So we'll use both ways to talk about it, so long as there's no confusion. We should be okay here. All right? Now, if you guys actually look at this is perfectly fine for the general case here. We've got a negative slope in this case. Do you remember from your previous classes? Slope was what? A measure of the steepness of a line. Okay, the steepness of a line. M was the change in y. Remember our notation for the change in y? We had delta y. Delta x would be the change in x. So this would be, if I had 2 points on the line, y1 minus y2 divided by the corresponding x values, x1 minus x2. Okay, let's take a quick example. Find the equation of the line containing the following 2 points. All right, we don't need to hear from kitties. Negative 1, 2, and 3, 11. Okay, this would be very easy here. It doesn't matter what order you take your differences to compute your slope, so long as you're consistent about it. So here's what I'm going to do. I'll go like this. 3 here. Let's start. I guess I'll go ahead and start with 11 here. I'll go 11 minus 2 for my change in the y values in these 2 points. The corresponding x value to 11 is 3, so I have to start with that since I started with 11 here. And then I'm subtracting negative 1. And you guys see that would be what? 9 over 4. So the slope of this line we're seeking would actually be 9 over 4. That means the different ways you could interpret that, every time I move 1 unit in the positive x direction, I move up 9/4 units in the y direction. Or another way to think about it, if I move 4 units in the positive x direction, I move 9 units in the y direction. Okay, so this is a very steep line if you were going to try to walk this or something. Let's go ahead. Do you guys remember, this is called slope-intercept form? Let's go ahead and express our answer this way. Slope-intercept form. That was our what? Y equals mx plus b. That's because you can see the slope right there and the y-intercept right there. For slope-intercept form, okay, I probably should have asked my question, telling you how to express your answer, but I'm doing it now, okay? So let's see. I've got y equals mx plus b, but I just computed m as being 9/4. What I don't know yet, my other parameter, is b. I need to compute that. Now, if you went ahead and computed the slope correctly, it should not matter which point you use to calculate what b ends up. Okay? Let's demonstrate that now. Let's go ahead and say we're going to use, say, 311. Okay? This is just saying when x is 3, y is 11. So we would go ahead and put those numbers in like that. And then b would be 11 minus 27 fourths, as you can see. This is really 44 fourths. So this is 44 minus 27 is 17. So this would be 17 fourths. So we have that second parameter. And it looks like this is going to be the slope intercept of our line. Okay? You ready? Just for the sake of completeness here, I'm going to use the other point and pretend we're starting over at this. Okay? So I've got y equals 9/4 x plus b. So I'll pretend I don't know what b is now. So we're starting over with that aspect of the problem. Let's go ahead and use, let's see, -1, 2. That was the other point, I think it was, wasn't it? Yes. Okay. So y is 2 when x is -1. So we're looking at this equation, solving for b. Okay, so you see b would actually be 2 plus 9/4 when I move this other guy over. Okay, that's really what? 8/4 plus 9 is 17/4. So we get y equals 9/4 x plus 17/4. Okay, so there's the equation of our line. Once again, exactly the same answer as we had previously. Okay, exactly the same answer as we had previously. I'm going to do a video later on about how you use Desmos to do linear regression. So we'll be looking at a few applied problems in section 4.2 dealing with linear functions in later. Okay, I want to go to 4.3 dealing with quadratic functions. What does a quadratic function look like? It looks like this. Y equals f of x, okay, equals a x squared plus bx plus c. Okay, a, b, and c are constants. Okay, a, b, and c are constants. X is the independent variable. It's the thing varying. One thing I would throw in here, generally a would not be 0. Otherwise, that term could disappear and we really wouldn't be dealing with a quadratic function at all. We'd be dealing with what? A linear function. Okay? So I'm just going to assume throughout that a is not equal to 0. Okay? You folks might know already that if you were to graph this thing, if you were to graph a quadratic function, what you end up getting is something called a parabola. Okay, let's put that down. The graph of a quadratic function is a parabola. Function is called a parabola, not parabola. Okay, and we'll go ahead and see what some of those look like here in a minute. Okay, a quadratic function, let's maybe adjust this. A quadratic function is going to look like this, kind of a smiley face, and it will have a vertical line of symmetry here. A smiley face if a is greater than 0, okay? And a frowny face, so it's going to be sort of frowning, if a is less than 0. Once again, still with the line of symmetry here. Now, the way to remember this is what? Positive people smile, right? Positive people smile. Negative people frown, okay? Negative people frown. So the leading coefficient, if the leading coefficient is positive, then it's what? It's a smiling parabola. If the leading coefficient is what? Negative, then it is frowning. It's opening downwards instead of upwards. Okay? So that's something we want to remember. Now, in either case, do you remember we talked about local minima or local maxima? Okay? In the case where it's opening upwards, where a is greater than 0, the vertex has a local minimum, which is actually what? An absolute minimum. This is called the vertex. Okay? And over here, where a is less than 0 and it's frowning, this has what? A absolute maximum, as far as the y values go, of course. It's also called the vertex, okay? So this vertex is going to be the local maximum or minimum, depending on the situation you're dealing with, okay? It turns out that the line of symmetry for the vertex always goes right through the vertex here. And we're going to see how we end up actually computing the vertex in each situation, and how we sort of get an idea what the graphs of these things end up looking like, okay? In fact, one of the first problems I want to start with then is finding the vertex, okay? Let's talk about finding the vertex of a parabola. I'll just say finding the vertex, since we know this is in the context of parabolas. Find the vertex, finding the vertex. Here I'm going to say this using the process of completing the square. Do you guys remember how that went? Completing the square. Okay. I'll show you guys how to do this. So when the time comes, you want to be able to do this, because I'll ask you a question about finding the vertex of a quadratic function, and I'll say this technique, completing the square. Okay? I'll show you another technique here in a minute, just a minute, but let's work on this now. Let's take an example. Y equals f of x, and it turns out this is really useful. We'll see later for finding the vertex in the second case here. But let's do this first. Okay? Y equals x squared minus 6x plus 1. Okay, suppose that holds. We know that's a parabola. If we were to graph it, it's opening upwards. Okay? And I ask you to find the vertex, and I want you to use completing the square. Okay? I'm going to show you guys how this works here. Here's what we're going to do. We're just going to go ahead and do this. We'll go y is x squared minus 6x plus 1. Okay? Now I'm going to take the easiest case first, where the leading coefficient is 1. And I'm going to factor that 1 out of both these terms. Let this guy just float down here, the constant term. Just factor it out of both the x terms. Okay, well, there's really not much to do if I was to factor 1 out. Okay, in fact, there's really nothing to do. Okay, well, don't worry about that part then. Now, do you guys remember the completing the square process in the case where you're dealing with a monic quadratic? Like this, monic, remember, leading coefficient is 1. You take half the coefficient on x and square it. Okay, what's half the coefficient of x? That'd be half of negative 6, and I'd square that, and I would get 9. Okay, you could, here's my thought cloud, I could just do that in my mind, but there it is. I'm going to write it for you. Now here's what I want you to do. I want you to add it to these two x terms. When I add that 9 to those two x terms, you know this is now going to be a perfect square. Okay, now I want this to be equal to the original. I want that to be a valid equal sign, right? Well, if I just went in there and arbitrarily added 9 to there, I better subtract that 9 also if I expect this to do what? Still be equal, right? These 9s would cancel. Of course, I don't want to cancel them. That's the last thing I want to do. Okay? Now, I said this should make a perfect square, right? Okay? And it does. It's, if you guys think about that, it's actually x minus 3 squared. And then over here, I get minus 8. Okay? Now, here's what's going to be my claim here. Okay? And then we'll generalize here in a little bit. Here's my claim. The vertex has the following coordinates. 3, where'd I get the 3 from? Right there. Not negative 3, positive 3, comma, negative 8. Yes, I retained the negative there. This is the vertex. 3, negative 8. Okay? Is this going to be a minimum or maximum point as far as y values go? Well, this thing was what? A was equal to, that's the leading coefficient, remember, ax squared plus bx plus c. A is 1, that's greater than 0, so this thing is opening upwards, right? It's smiling. Positive people smile. Therefore, the vertex is going to be what? A minimum. In fact, its coordinates is going to be 3, comma, negative 8. The line x equals 3, that vertical line through the vertex is going to be the line of symmetry here. Okay? Now let me go ahead and make an argument why. Okay? All right, everybody? This is really my final answer, but I want to circle that because I want to point this out here. Okay? Now remember, that's really just we've rewritten f of x is really what we did. We just rewrote the function in this funny way. And here's my argument here. Okay? If x is anything different than 3, then x minus 3 squared is greater than 0. Does that make sense? Well, it should, because if x is different than 3, then x minus 3 is not 0. It's not 0. X minus 3 is not 0. When I square a non-zero number, I always get what? A positive 0. A positive number, right? So this has got to be true. And now when I subtract 8 from this thing, I would get what? X minus 3 squared. Here, let me write this. That's got to be greater than negative 8, right? Just subtracting 8 on each side here. Okay? But I would point out that the function evaluated at 3 is actually negative 8. What if I evaluated f at 3? If I put 3 in there, this would zero out, and I would end up with negative 8. So this is actually the function evaluated at 3. I almost wrote negative 3 there. Okay? Now I just want you guys to think about the reasoning here. If x is different than 3, then the function evaluated at x is greater than the function evaluated at 3. Therefore what? Therefore, f of x has a minimum value of negative 8 at x equals 3. Okay? Hope that makes sense. Alrighty. And what about this symmetry thing here? Let me show you what's happening with the symmetry. You know, if, let's try the symmetry here. You guys remember I said this would be symmetric about what? X equals 3. Okay, x equals 3. Well, let's say x is equal to 3 plus some delta x. Now, delta x may be, what, positive or negative here, okay? But it's some change in x. Remember how we were using that notation, delta x? Okay? My function evaluated at x would be what? 3 plus delta x minus 3 squared minus 8. The 3's cancel, and I would get delta x squared minus 8. Okay? Now, do you guys notice here, if the delta is same, whether positive or negative, I get the same value when I square this. So, you guys see what I mean? If I go f at 3 plus delta x, I would get exactly the same thing if I went f at 3 minus delta x. That would mean if I move what? Delta units in either direction, from 3, I get the same function value because the difference is being squared here. Okay? That's why you're getting this symmetry around the line x equals 3 in this particular case. Okay? Let's do a second example of finding the vertex of a parabola by completing the square. When the time comes, I will have all the details written out telling you exactly the method I want you to use. I'm a little lazy right now because you know the context here. Anyway, let's come over here. Just for practice here, you guys see that A is 2, that's the leading coefficient, what I was calling that. B is -4 and C equals 7. Okay, so far we really haven't worried about these. That's the main fella. Is this going to be opening upwards or downwards? You know what? I think I'm going to change this. There you go. There. Let's make it. It's going to be opening downwards because I made it a negative suddenly. Okay, but that'll be fine here. Let's go ahead and find the vertex, and let's see what happens here. Here's what I want you to do. Y is -2 x squared minus 4x plus 7. So I'm pretending I'm starting my work on my page for an exam or something. I'm going to just let this guy float out there, the constant. I'm going to take the a and factor it out of the first two terms, that is the x terms if it's written in descending order. We'll talk more about descending order and stuff in the next section. Okay. Do you guys see if I factor out that -2 there, I get -2 times the quantity x squared plus 4x. Okay, now what I want you to do is complete the square on that fella. Okay, how do you complete the square on that? You would take what? Half the coefficient on x and then square it. This is going to work because what I've done when I factored out the a here is I have a monic quadratic inside the parentheses. See that? That's 1. That's the magic number I want to add in there to make this thing a perfect square. Okay? So again, you could do this just in your mind if you want. You don't have to actually write that calculation. But it's a little different. Doing and teaching are two different things. Anyway, I want to add that 1 to these two fellows. Now that should be a perfect square. Now I can't just jump in there and add something without what? Screwing up my equal sign, unless I do what? Compensate for what I did. Okay, so I am going to compensate for what I did. I added 1 and then I'm going to subtract 1. Now I want to retain all this stuff, for goodness sakes. Okay, I just went in there and worked for that. I don't want to throw it away now and combine those and cancel them. That's the last thing on earth I would want to do. Here's what I want to do. I'm going to retain that -2 out front. Right here, do you see that's actually x plus 1 quantity squared? Okay? Now, don't forget here, too. Here's where sometimes people mess up here. I want to bring that outside the parentheses here. I'm getting rid of parentheses on this part. Okay? I'm going to go -2 times -1. Because don't forget, everything inside the parentheses here is being multiplied by -2. So -2 times -1 is +2. And then I'm still retaining that 7 there. So now my function actually looks like this. It's -2 x plus 1 squared plus 9. Okay? And now, by arguments similar to what I had before, my vertex is going to be -1, 9. Okay? Where's that thing equal to 0 inside there? -1. Okay? I'm going to be writing this a little more explicitly, this sort of general case here. And there we go. Is this going to be smiling or frowning, we said? Well, the leading coefficient is -2, so it's going to be frowning. It's going to be looking like this. So the vertex is going to be a high point, a maximum, that is, for this. And it's going to be symmetric around the line x equals -1 by arguments similar to what I just did previously. Okay? Okay? Now, you guys might wonder why this is -1. Let me show you here what's going to happen in general. Okay? If I've got a quadratic like this, ax squared plus bx plus c, and then I'm going to write, this is sort of, I guess this would be standard form. This is standard form. You guys have all seen that before. similar to what we do with quadratic equations and everything. Let's talk about vertex form. This is y, it's f of x. All it is a matter is rewriting this like we've been doing. Ax minus h squared plus k. And the vertex ends up being h comma k. I've actually used this little fact here in my last two examples. Okay, in my last two examples. Okay? Remember how I used completing the square to rewrite the first one? Okay? What would my h be here? If it's x minus h squared, don't forget your a's in front there. You still got that leading coefficient. Okay? What would my h be here? My leading coefficient is actually 1. People don't usually write that. My h would have to be 3. Don't forget it's x minus h. And then it's plus k, though, so that would be what? Negative 8. Okay, so my h and my k are 3 and negative 8, respectively. In this previous problem that we just did, example 2, that would be what? If I wanted to write that as x minus h, that would have to be what? X minus negative 1. That means my h is negative 1. My k, because it's plus k, my k would end up being 9 here. Okay? Now, arguments similar to what I just did before, right? Why this ends up being a vertex. If a is greater than 0 and let's take the case where a is greater than 0. We know it's saying opening upwards. I claim this is hk. A is greater than 0, or what? If a is less than 0, it's frowning. Okay, it's easy to see by something we call M behavior. We'll see later. And also just plotting points. You'll see this has to happen here. Okay, anyway. Come back over here. If I take any value of x different than h, different than that x value of the vertex, and it's opening upwards like this, if x is different than h, then x minus h squared will be positive again. I multiply by a, but a is positive. I get a positive number being added to k, but the function evaluated at h is obviously k, so that means this has got to be a minimum here. Okay? Then in a case where a is negative, you create a similar argument, and you find out that what? In fact, in the case that it's frowning, this has got to be a maximum for that parabola, a maximum value for the function. All right? All right, let's discuss now the general case of finding the vertex using completing the square. This is going to essentially give me, in the end, a formula for the vertex in terms of the parameters a, b, and c of the quadratic function. All right? Now, I'm going to be going like this, ax squared plus bx plus c, and this time it's going to be really convenient to give that a name. We'll see here in the end when I create my formula. Anyway, let's go ahead and do this. Now I'm going to complete the square on this. Remember how that goes. Now I'm doing this in general. Do you remember I said I'm going to factor the leading coefficient out of the first two terms and then just let the constant term float there. So I've got that. Now I can divide that a out because you remember originally we were assuming that a is non-zero. So we should have no problem doing that. Now this time I'm going to go ahead and think about the magic number I want to add to these two terms to make it a perfect square. You guys remember I would take half the coefficient on x. So here's my coefficient on x. If I take half of that, that would be what? Multiplying by a half. Okay, that would just double the denominator. And then what did I do to it? I squared it. So that would be b squared over 4a squared. Okay, now what I want to do is take that magic number, I want to add it inside there. And once again, I need to compensate for the fact that I added it in there by subtracting it. And then just like the last problem, I'm going to gather these together here. If you guys think about this for just a moment, these three terms are actually the square of x plus b over 2a. Okay? Now don't forget that a is multiplying on everything inside the parentheses, so when it multiplies on this term right here, I'm going to have what? A over 1 multiplying on this, since that's really a, and I would get ab squared on top, and that a on top could cancel with 1 on the bottom, one factor of a on the bottom or in the denominator, and then I would get that. Okay? Alrighty. So that's why I only have a first power on a in the denominator in the term now outside the parentheses. Okay? Now let's keep going. If you want to, you can write the following here. Subtract b squared minus 4ac all over 4a. Here I just went like this. This is actually what? 4ac over 4. The double negative makes it positive there, so I'd be subtracting that whole thing. So this is actually my function, f of x. Okay? Now, this is supposed to be a times x minus h squared plus k. That would mean my h is actually what? My h, this implies h is, don't forget that's a minus h here. H is actually negative b over 2a. Okay? My k would be all this gobbledygook. Okay? All this gobbledygook. I don't want to remember it that way. You know what I'm going to do that way? I'm going to be something a little more efficient here. I'm simply going to say f is the function evaluated at h. Well, that has to be true, right? Because the vertex certainly lies on the graph of y equals f of x. So if our x value at the vertex is h, the y value has to be the function evaluated at h, doesn't it? That way I don't have to remember this stuff. Okay? So here's our formula for the vertex. If I've got y equals f of x is ax squared plus bx plus c, the vertex is going to have these coordinates. The x coordinate is going to be negative b over 2a. The y coordinate is going to be the function evaluated at negative b over 2a. This is much easier than memorizing the formula for k that we would have had here. You know, this stuff. Yeah, I don't want to bother doing that. Now, by the way, negative b over 2a, that shouldn't be so hard to remember, should it? Do you guys remember the quadratic formula? You guys remember the quadratic formula? If I was to set something, set this equal to 0, what would I get? X is negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay? Now for the vertex, just forget all that quadratic surd part. It's just the x-coordinate is negative b over 2a. Oh, by the way, you could see here for if you have two real x-intercepts here, the vertex ends up having an x-coordinate, which is the average of these two. But we could talk about that later. Anyways, so I hope you understand this. Definitely memorize this thing. Okay? Now we're going to do a problem here in a second. Let's do this example, which I'll call example 3 here. Find the vertex of y equals f of x equals 2x squared minus 5x plus 1. This time I'm not going to be using completing the square. Instead, I'm going to be using the formula I just developed here a few minutes ago. This thing. Okay? Let's go ahead and identify the parts and pieces. A is 2, B is negative 5, and C is 1. Okay. So all we have to do is the following. I'll call the x-coordinate of the vertex h again. That's negative b over 2a. So that would be what? Negative, here's b over 2 times 2. And that looks like what? Positive 5/4. Okay. How do I find the y-coordinate? What I'm calling the k. That would be the function evaluated at 5/4. So just go ahead and stick 5/4 into the function and evaluate, and let's see if we can't work this out here. Okay. 5 squared is 25. Okay. 4 squared is 16. I've got a 2 out front. So isn't that really 25 over 8 when I reduce it? Okay. Minus 25 over 4 plus 1. You can see the least common denominator is going to be 8. So let's maybe do this. Minus 50 over 8 plus 8 over 8. So I've rewritten those all in terms of 8s. Okay. So I've really got 25 minus 50 is negative 25 plus 8. Okay. 8 minus 25, I think, is negative 17 over 8. Okay. So here's the vertex. It's going to have coordinates 5/4, comma, negative 17/8. Okay. Let's maybe throw in a couple other things I didn't ask here. What's the axis of symmetry? That's the vertical line going through the vertex. That would simply be what? X equals 5/4. Now remember, that's a line, so it's the set of points x, y in the Cartesian plane whose x coordinate is 5/4. Okay? Now is this a minimum or a maximum? Okay? Well, this is opening upwards, right? Because a is greater than 0. A is 2, which is greater than 0. So it's opening upwards, so this is a minimum. The minimum value of y, value of f of x, let's say instead of y, is negative 17/8. So that's a minimum value. Okay? So there we go. It's really not too hard if you remember the formulas.